Hello, calculus students. In this video, we're going to take a look at our 7.2b notes, finding volumes of solids with known cross-sections. So unlike the last lesson where we had solids that were obtained by taking a region and rotating it about an axis, what we're going to do this time is we're going to take a look at some solids where we know what the shapes of their cross-sections would be. So suppose you wanted to find the volumes of the shapes below. Notice that the slices or the cross-sections are perpendicular to the x-axis, or that are perpendicular to the x-axis, are common shapes. They're prisms or cylinders whose bases are familiar. They're semicircles or they're triangles or they're rectangles. So if you can look in this picture, we can see how that cross-section is like half of a cylinder whose base is a semicircle. Here we have a cross-section that's a triangle. Here we have a cross-section that's a rectangle, okay? So those cross-sections are shapes that are familiar, and then we can find the volume of these little teeny tiny three-dimensional shapes that are cross-sections by using familiar formulas. Okay, so just as the disk mesh method was used to find the volumes of solids formed by rotating a region about an axis by adding the volumes of circular cross-sections, long sentence, the volumes of these solids can be found by finding the sums of the volumes of their known cross-sections. All right, so let's take a look at the formula, and then we're going to try some examples. So volumes of volumes of solids with known cross sections. So for a cross section of an area, for volumes where the cross section, which we're going to call A of x, is taken perpendicular to the x-axis. In this picture, it's kind of tiny, but you see this teeny tiny x. Okay, so there's the x-axis and here's the y-axis. So you can see that this cross-section is perpendicular to the x-axis. So if that's the setup, then here's how you would find the volume. The volume would be an integral from a to b. Now, those are x-bounds. So from a to b, those would be from here to here. Okay, x-bounds, it's kind of hard to see in this picture. A to b of capital, whoops, that's not what I meant to do, sorry. Capital A of x, that would be the area of the base of this three-dimensional slice, and then we need to multiply it by the height of that three-dimensional slice, which would be a delta x, and in our integral we represent that with dx. All right, so in other words, this A of x, that would be the area of one cross-section perpendicular to the x-axis. So that's the area of a cross-section, or a slice, if you want to think of it as a slice, that would be perpendicular to the x-axis, all right? And then the dx, that represents, let's just call that the thickness of that slice, or of a cross-section. All right, and then of course, as we increase the number of cross-sections, that thickness would get thinner and thinner and thinner, and then the sum of those volumes then approaches the volume of the actual solid. All right, and so then if we have a solid where the cross-section, the cross-section, for cross-sections of area of A of y, these cross-sections are taken perpendicular to the y-axis. So then, again, if you look at the picture, here's your x-axis and here's your y-axis. So you can see how these cross-sections are perpendicular to the y-axis. Then to find that volume, we would take the integral of, let's call these, since we want to differentiate between our x-bounds, let's call these y-bounds c to d of A of y dy, where again, this A of y would be the area of a cross-section that's perpendicular to the y-axis, and then the dy would be the thickness of that cross-section. In this next part of the video, you can just relax. You don't need to take any notes. I just want you to watch and listen. We're going to look at an example of how we can use calculus to find the volume of this strange shape. This is, we could call it a semi-pair if we wanted to. It's half of a pair. And before you knew some calculus, there would have been no way that you could have found the exact volume of this half a pair. You could have come close by maybe finding some approximations, but there are no geometric formulas for finding the volume of half of a pair. So what we're going to do is take a look at how we can use calculus and find the volume of the solid because we would know what its cross section would be. So let's first take a look at what the base of this solid would look like. So in this photo, you can see that you don't see the pair anymore. All we see now is the shape of the base of that pair. So in the next slide, we're going to take a look at how we can use cross sections. In this picture, you can see that the cross section is a familiar shape. It's what we call a known cross section. The cross section of this pair, here let me just outline it for you, would be a semicircle. And that's a shape that you are very familiar with from geometry. So now let's use this example of one slice or one cross section and see how we can use it to find, well, not just this one cross section, but the sum of an infinite number of cross sections to find the volume of this half of a pair. So to find the volume of this one cross section, now this one cross section, it's half of a cylinder, isn't it? Its base, remember, was that semicircle, okay? And then it has a teeny tiny little height, which is the distance from one base to another. So to find the volume of this slice of a pear, we would take the area of the base and then multiply it by its height. And then imagine adding up an infinite number of those. That's what an integral is. It would be the sum of an infinite number of these cross sections that would give us the volume of the entire half of a pear. So to find the area of this base, we need to find the radius, which would be from here to here. Okay, that is our radius. Okay, so how am I going to find the radius? Well, the radius would be half of the diameter. So how can we find the diameter? Well, let's give some names to some functions here. This is in an xy plane. This is our x-axis. This is our y-axis. So let's go ahead and name this top function. Let's call it f of x. Okay, and then let's call the bottom function, let's call it g of x. All right, so if we were going to find the diameter of this this slice, this semicircle, that would be the distance from our f function to the g function. So to find the diameter, let's see, the diameter would be f of x minus g of x. Okay, so if that's our diameter, then the radius would be half of that. So the radius would be f of x minus g of x, and then we need to take half of that. Okay, so now that we have the radius, now we can find the area of the base of this little half of a cylinder. So the area of this base. So what would that be? That would be half of the area of a circle. So the area of that base would be equal to pi r squared, but we don't want the entire circle, we just want half of that. So in this case, that area would be equal to 1/2 times pi times, remember how we found the radius we had right here, it's f of x minus g of x all over 2. So f of x minus g of x, okay, all over 2, and then we need to square that. So what do we have then? We have 1/2 pi times the radius squared. That would give us the area of this semicircle. Okay, so now let's talk about how to find the volume of the entire semi-pair or half a pair. So in general, remember, to find the volume of a solid with a known cross-section, we would take an integral from a to b of a of x, which is the area of that cross-section, and then times dx. Remember, dx represents our delta x, which is right here, this distance from one base to another. Let's just go ahead and label that. This little skinny height, that is, let me put a different color, that is delta x. All right, so the volume then of this half a pear would be the integral from, now since we're going to be integrating with respect to x, I need x bounds going from a to b. So let's go ahead and just in general, of course this left bound looks like it's 0, but let's just call it a, and then this right bound here, let's call it b. So we're going to integrate from a to b of the area of our base. Well, we've already done that work. That was right here. This is the area of the base. So that would be, let's see, 1/2 times pi times f of x minus g of x. And that's all over 2. And then we're going to square that, okay? And then don't forget your dx. Remember, the dx represents this distance from one base to another. So dx. All right, and that's how we would find, if we were given these function values, we could, of f of x and g of x, we could actually find the volume. But in general, I just wanted you to see this setup. Let me go ahead and just put a box around that. That's how we would find the volume of half of a pear. Okay, so back to our notes. By the way, when I was done taking pictures of the pear, I ate the pear and it was delicious. But anyway, back to our notes. In this first example, we're just going to set up the integral that would find the volume of a solid whose base is the area bounded by the graphs of y equals x squared and y equals negative 2x plus 3. Now, what you're looking at right here, you don't see the whole 3D solid. You just see the shape of the base. It's kind of like when you looked at the outline for the half of a pear. They're just looking at the shape of the base. And so that's what the base shape looks like. And its cross sections are perpendicular to its cross sections that are perpendicular to the x-axis are the following shapes. Well, in our first example, we're going to let those cross sections be rectangles of height 4. So what I want to attempt to do, I'm going to stop the video and I'm going to try to draw what you're looking at. These little rectangles that you see are actually the bases of those cross sections. So let me see if I can sketch kind of what this would look like in 3D. Okay, so that's my best attempt to draw what we're actually talking about. So you can see the shape of the base of our three-dimensional solid, and then these cross sections are going to be rectangles. Okay, so as you look at the picture here, this rectangle, or that distance right there, would be the same as the base of one of those rectangles. So keep that in mind as we try to find the volume. So first of all, let's start by writing our formula. To find the volume of this solid with a known cross-section, we're going to take the integral from a to b of a of x dx. So a of x is the area of, in this case, of a rectangle. So let's draw a rectangle, and let's talk about how to find its area. So remember, this yellow right here is this distance. So let me go ahead and shade that in yellow. So that would be this distance. All right, so let's talk about how we can find that distance. Well, as you look at the graph, as you look at the xy plane, this yellow distance would be the difference of the top function, which is negative 2x plus 3, and the bottom function, which is x squared. So what we're going to do is we're going to take that top function, which is negative 2x plus 3, and then we're going to subtract from that the bottom function, which is x squared. Okay? Now, that would be this distance, the yellow distance. And then remember, we were told the height of each one of these rectangles. So here's the yellow distance. The height of each rectangle would be 4. So that would be, from here to here, would be 4. All right, so what is our a of x? How do you find the area of a rectangle? Well, you just take its base times its height. So I'm going to go ahead and distribute. I'm going to take 4 and multiply it by all 3 of these terms. So that area would be negative 8x plus 12, let me fix that real quick, plus 12, and then minus 4x squared. All right, so now we're ready to write an expression, the integral that would find this volume. So that volume is going to be the integral from a to b. Now, remember, we're differentiating with respect to x. So I need x bounds. I need this leftmost x bound and this rightmost x bound. Now the way we'll find those bounds is by taking these two equations and setting them equal to each other. So I'm going to see if I can squeeze that in this little box here. I'm going to take x squared and set it equal to negative 2x plus 3. Now this is a quadratic equation, so let's get it in standard form. And it would look like x squared plus 2x minus 3. I just moved those terms over to the left is equal to 3. And then let's factor that trinomial. So that would be, let's see, x plus 3, x minus 1. So it looks like our solutions for x are negative 3 and 1. So our left bound here would be at negative 3, and then our right bound would be at 1. So we're going to integrate from negative 3 to 1, and then we need to take a of x. So remember, we figured out what a of x it was right here. So let's put that in some parentheses and write negative 8x plus 12 minus 4x squared. Let's close those parentheses, and then don't forget about your dx. All right, so that's how we would find the volume, and we're not going to worry about finding an exact answer at this point, but that's how we would find the volume of a cross-section that has, the volume of a solid whose base is this shape, okay? If you were looking at it like if it were sitting on a glass coffee table and you could lay under the coffee table and look up at it, that's what the base would look like. And then its cross sections are these rectangles, all right? So that's how we would find its volume. So now let's take let's talk about a different solid whose base has the same shape, but this time the known cross sections are semicircles, all right? So as you think of this yellow shape, now this is the diameter of a semicircle. So let me pause the video and see if I can kind of get a picture of that. Okay, bear with me. This is the best I could do. So again, here's the shape of the base of our three-dimensional solid, and then the cross sections are these semicircles. All right. So let's talk about how we would find the volume. Now, again, as you look at this picture, okay, this yellow rectangle, this yellow distance from one function to the other would be the base or the diameter of one of these semicircles, all right? So let's go ahead and draw a semicircle here, okay? And I'm going to, again, highlight this base, this yellow part, so you can see that the way we find that yellow is by taking this top function, which was negative 2x plus 3, minus the bottom function, which is x squared. Okay, so this distance, this diameter right here, this diameter then would be the top function, which is negative 2x plus 3, and then minus the bottom, oh, whoops, I forgot my 3. Sorry about that. Negative 2x plus 3, and then minus the bottom function, which is x squared. Okay, so now to find the area of that semicircle. Okay, this is kind of like what you did with the pear example, because remember the cross sections of the pear were semicircles also. We're going to take half of the area of a circle. So that would be 1/2 times pi times the radius squared. Well, the radius is going to be half of this. Remember, this was the diameter from here all the way to here, so it's half of that. So that would be negative 2x plus 3 minus x squared all over 2. That's our radius, and then we need to square that, okay? So how are we going to find the volume then of the solid whose base is this shape and whose cross sections are the semicircle? Okay, we're going to let v equal the integral from. Now, these would have the same bounds as the rectangles. The bounds don't change. They would still go from negative 3 to 1 of 1/2 pi times the radius, which is negative 2x plus 3 minus x squared all divided by 2. That's your radius squared. And then don't forget your dx. And then I'm going to simplify this a little bit, because remember, constants can all be pulled out in front of the integral. So in front of our integral going from -3 to 1, I'm going to take this 1/2 pi and pull it out in front. And then I'm also going to take this denominator of 4 that's being squared. I'm sorry, I was thinking ahead. This denominator of 2 that's being squared. 2 squared is 4. So I'm going to take the 4 and multiply it by this denominator of 2, which is give me 1/8. I'm going to pull that 1/8 and the pi all out in front of the integral. So it would be 1/8 pi of -2x plus 3 minus x squared all squared dx. So this would be the integral that would give us the volume of this solid, of the solid that has this shape for its base, and its known cross sections are semicircles. In example 2, we're asked to set up an integral needed to find the volume of the solid whose base is the area bounded by the circle x squared plus y squared equals 9, and whose cross sections perpendicular to the x-axis are equilateral triangles. So here's my attempt of drawing what would be going on here. The base of this solid is a circle, and then the known cross section would be these equilateral triangles. All right. So let's see if we can find the integral that would find that volume. Just as a reminder, you might remember this from geometry, that the area of an equilateral triangle is a side of that equilateral triangle squared times the square root of 3 over 4. Again, where S is the side of the triangle. Okay, so let me grab a highlighter. Okay, and just highlight this, what we're looking at here. What that would be the base of an equilateral triangle. It would be one of these bases right here. So let me draw an equilateral triangle. Okay, and then I'm going to highlight its base yellow. Whoops, I missed. Sorry about that. Okay, let me highlight its base in yellow. Okay, so this base, what you're looking at right here, is the base of one of these equilateral triangles. All right. So to find the area of the triangle, we need to know what S is, the length of one of the squares. So let's label this. This length would be S. So how are we going to find that? Well, if you look at our XY plane, to find the length of this yellow segment, we just need to take the top of the circle, that function definition, minus the bottom of the circle. So what we're going to have to do is take this equation, which is not solved for y, and we're going to have to solve it for y. So I'll just do that right here. We have x squared plus y squared equals 9. Okay, if we're solving that for y, we'd want to subtract an x squared from both sides. And then we'd take the square root of that, both sides, and we would get that y is equal to plus or minus the square root of 9 minus x squared. In other words, this top part of the circle, its function definition is positive 9 minus x squared, and this bottom part of the circle, its function definition is negative 9 minus x squared. Okay, so if I wanted to find this distance from here to here, I would take the top function minus the bottom function, or square root of 9 minus x squared minus a negative square root of 9 minus x squared. And remember, when you subtract a negative, it's the same thing as adding a positive. So in other words, this distance, this yellow distance then, would be 2 times the square root of 9 minus x squared. Again, that was because I took positive square root of 9 minus x squared minus a negative square root of 9 minus x squared. And subtracting that negative is the same thing as adding a positive. Okay? So now let's figure out what a of x would be, the area of that equilateral triangle. Well, using this formula again, we're going to take our side. This is the measure of a side. We're going to square it, multiply it by the square root of 3, all divided by 4. So that would be the square root of 3 over 4 times 2 times the square root of 9 minus x squared, and then square all that. And then we could simplify that a bit. Let's see, this would be the same thing as the square root of 3 over 4 times, if I were to square this 2 times the square root of 9 minus x squared, I would get 4 times 9 minus x squared. Squaring that radical gets rid of the radical, and then of course 2 squared is 4. Then I can cancel these 4's, and this will simplify to the square root of 3 times 9 minus x squared. All right, so kind of running out of room here, so let me make us a little bit of space here to find the volume of the solid whose base is a circle and whose cross sections are equilateral triangles. That volume would be the integral from a to b. Now, what do you think our bounds are? Our left bound looks like it's going to be -3. The right bound would be +3. Okay, and we could find that easily by putting a 0 in for x to find out what. No, I'm sorry, a 0 in for y to find out what our x values would be. Well, if y were 0, x squared is 9, so x is plus or minus 3. So our bounds go from -3 to 3 of a of x, which is the square root of 3 times 9 minus x, the whole thing. Oops, I made a mistake, didn't I? So let me fix, you might have noticed this over here. This should have been 9 minus x squared, like that. Okay, so let me fix the mistake here. Sorry about that mistake, by the way. Oh, it's not going to erase, so that's okay. We'll just go x squared. And then don't forget your dx. And then I'm just going to simplify that a little bit more. I'm going to go ahead and pull this square root of 3 since it's a constant. Let's pull it out in front of the integral symbol. So we have v equals the square root of 3 times the integral from -3 to 3 of 9 minus x squared dx. Let's take a look at one more example. This time in example 3, in example 3, we're told that the base of a solid is bounded by y equals x squared, the line y equals 0, which is the x-axis, and then this vertical line x equals 2. And for this solid, each cross-section perpendicular to the y-axis this time is a square. Okay, so what you're looking at, this little rectangle is actually the base of a square that's like, if you can think of a square that's coming straight out of the screen. So it says, set up the integral needed to find the volume of this solid. Okay, so this time, since we are going to be looking at cross sections that are perpendicular to the y-axis, our volume is going to be an integral from c to d, where those are d bounds, of a of y dy. All right, so let's draw a picture of what our cross section would look like. Well, we're told that our cross sections are squares. Okay, so this whoops, I missed it again. I don't know why I'm so bad at highlighting. Sorry. Okay, this yellow section is the bottom of a square. Again, if you can picture that square coming straight out from the screen. And so to find the area of that square, all we need to do is take a side. We need to take a we need to take a side, and then we need to square that side. Okay, so we need to figure out what this length would be. This length of a side. Well, the length of the side is this right here. So since it is parallel to the x-axis or perpendicular to the y-axis, to find this length, we need to take a right minus a left, a right function minus the left function. So that would be, this function, remember, was 2, and this function, now, we got to stop for a second here. We were given y equals x squared, okay, but I need to define this function as a function of y. So let's take that y equals x squared and let's solve it for x. So we would do that by taking the square root of both sides. So x is equal to the square root of y. We don't need the plus or minus this time because we're just looking at this part of the function. Okay, so that means that this yellow measure right here, we need to take 2 minus this function, so that would be 2 minus the square root of y. All right, so how would I find the area of that square? My a of y then would be 2 minus the square root of y, and then we need to square that. So to find the volume, we will take the integral from, now I need y bounds, okay, since we are integrating with respect to y, make sure that we have y bounds, so that they would start from 0 to 4, looks like, from 0 to 4, okay, so we would integrate from 0 to 4, and then a of y is 2 minus the square root of y, the whole thing squared, and then don't forget your dy. All right, so this expression represents how we would find the volume of a solid that has this shape for its base and whose cross sections are squares. All right, and then I just want to finish, I just want to show you a picture that I found on when I Googled. Here would be a project somebody did where you could see how when you take these cross sections, in this one our cross sections are semicircles, here it looks like the cross sections are rectangles, here the cross sections are triangles, and it looks like these cross sections are rectangles. But again, if you look at an infinite number, well, not an infinite number, but it's approaching an infinite number of cross sections, you can see what these three-dimensional shapes would look like that have a base that has a strange shape, but the cross sections are something that are known. All right, so I don't know if I left this on your we're going to be working on, if your notes say homework, I think I might have taken that off. We will be working on homework in class next time. So if you have any questions over these notes, you can be sure and ask me then.